Welcome to the lecture on free vibration of single degree of freedom systems. Today we will discuss the energy methods. We already discussed in the previous lecture the case of free vibration using the Newton's law. We wrote the equations of motion, we found the natural frequency. Here there is another method, that is energy method. With the help of this method we can also get the natural frequency of the system. So here we know that if we have a system consisting of only the stiffness and mass, okay, and we disturb the system, it will vibrate with its own natural frequency, and this is the case of free vibration. Here the energy is neither dissipated nor supplied from the external force, so the total energy of the system remains conserved. That's why these systems are called the conservative systems. Mass has a kinetic energy due to its own velocity, and the spring stores the potential energy due to when it is stretched. So the sum of these two energy is constant for a conservative system. So the principle of conservation of energy we can write as T plus U equal to constant. So here we have T is the kinetic energy and U is the potential energy. So this is our system. Let's say this is so this total T plus U equal to constant. Now if we take a case of case such that let's have so this T plus U is constant at any instant of time T. Now let's consider two instants of time, so 1 and 2. So T1 plus U1 equal to T2 plus U2. So we have, let's have, this is our system. So this is a pendulum and this pendulum is vibrating. So let's say at any instant of time, here T1, here T2. So we have total and this is, let's say this is 1, 2. So T1 plus U1 equal to T2 plus U2. Now if we take this example, we see that at this point the potential energy is minimum and kinetic energy is maximum. Similarly, when it is at maximum of its displacement, here the kinetic energy is 0 because velocity comes 0 and potential energy is maximum. Similarly, in this case, when it go to maximum, this is equilibrium position, it is going to its maximum here x. It stops and that it come back. So here it has only potential energy, okay. So we are saying that when potential energy is maximum, kinetic energy is T is 0, and when T is maximum, its potential energy is 0. So if we put these two conditions in this equation, so let's take this first case when u max and t equal to 0. So 0 plus u max equal to the second case, this when we have t max and plus u is 0. So from here we can write that u max equal to t max. So this is Rayleigh's energy method. This is called Rayleigh's energy method. Now, in order to get the equation of motion, for any system we find its total at any general instant of time. We find the total kinetic energy, then total potential energy, and we write this equal to constant. Then we write d by dt. We differentiate it, t plus u equal to 0, because it is constant term, so its derivative with respect to t will be 0. So now we will take one example to find the natural frequency of the system using the energy method. If we take the simple example of a spring mass system, so let's take the example of a spring mass system. So we have, this is m, this is k. So we displace here, it is x stat. So at this instant the kinetic energy T equal to half m, this is m, v square, so x dot square, and potential energy U equal to half k x square. So here we can see that this is the potential energy half k x square in the spring, stored in the spring at this moment of time, and this is the kinetic energy. Now T plus U equal to constant. So T is half m x dot square and U is half k x square. This is equal to constant. So here now differentiate with respect to t, the time. So it is half m, this is 2x dot into x double dot. So this is 2x dot and then differentiate x dot, so it will be x double dot plus half k. Now x square, so it is 2x into x dot, and this is constant, so it is 0. So this will be cancelled out. So we will get, and x dot here, so we can leave this term. So we will have mx double dot plus kx equal to 0, or x double dot plus k by m x equal to 0, or x double dot plus omega n square x equal to 0. So here we get omega n equal to root k by m. So by using the this energy method, we reached to the same equation of motion of this spring mass system that we obtained using the Newton's law of motion. So now we will this is the simple system. Now we will take one more system. So let's take another system. So here we take a spring that is not massless. This spring has mass density, that is mass per unit length. So let's say it has a mass per unit length. So it has rho equal to mass per unit length, and this is the length L of the spring when it is in the equilibrium position. So this is in the equilibrium or unstretched position, equilibrium position. This is M. So the total mass of the spring Ms equal to rho into L. So it is rho into L. Now we disturb this system so to vibrate. So let's say here, and here we take a distance y, here element dy. So this is element dy. Okay. So the potential energy and kinetic energy we have to calculate. So here the kinetic energy of the mass, that is we say T m equal to half m into x dot square. So we assume that here it is x dot x, this velocity. Now we have to obtain the kinetic energy of the spring element. So we have taken a spring element. So the kinetic energy of the spring element. So dt s equal to, so half m, so m of this element is rho into dy, this is m of this element, into x, the velocity. So velocity, because here it is 0 velocity and at this end it is x dot. So the velocity at this y from the support will be y by L into x dot. Okay. So here this will be the velocity at this point. So it is y by L into x dot, because here the velocity is x dot, here it is 0. So here it is x dot. This is the kinetic energy of the spring element. So the potential energy of the system, of the system, because this spring is stretched with x total, so we will have potential energy U equal to half k x square. Now we have to find the total kinetic energy, because the total kinetic energy comprises the kinetic energy of the mass and the kinetic energy of the spring. So here the total kinetic energy of the system T equal to kinetic energy of the mass Tm plus kinetic energy of the spring, and we can integrate these from 0 to L, because this kinetic energy is only for defined for the elementary length dy, and if we want the kinetic energy of the spring, we have to differentiate from 0 to L. So we assume here t in y equal to 0 and y equal to L. So Tm equal to half m x dot square, and here 0 to L dts. So dts we can write here half rho dy y by L x dot square, half m x dot square plus half here rho by L and x dot square, that can be out because only we have the derivative with respect to y, and 0 to L y square dy. Okay, so we have written this y square, and here L square, so this is L square will be out, half rho by L square into x dot square. Now we will do this integral. So half m x dot square plus half rho by L square x dot square, and this is y cube by 3, and we have limit 0 to L. So we can find t equal to half m x dot square plus half rho by L square x dot square, and this is y cube by 3. So if we put the limit, so L cube by 3 minus 0, y equal to 0, so it is L cube by 3. So we can solve it. So it is L square cancel out, so here it will be only L, so we will have half m x dot square plus half here rho L by 3 into x dot square. Now rho into L is ms, so the total mass of the spring. So we can write half m x dot square plus half into rho L is ms by 3 x dot square. So we can write half m plus ms by 3 x dot square. So this is the total kinetic energy of the system, that consists of the kinetic energy of the mass and the kinetic energy of the spring. Now we will apply the energy method. So energy method say that T plus U equal to constant for any system. So T plus U equal to constant. So here T is half m plus ms by 3 x dot square plus U is half kx square, half k x square equal to constant. Now we differentiate both sides with respect to time. So here we will have half m plus ms by 3 into here 2 x dot into x double dot, 2 x dot into x double dot plus half k 2x into x dot, 2x into x dot equal to 0. So here 2 cancel out, 2 cancel out. So here m plus ms by 3 x double dot, because here is x dot, that will be gone, plus k x equal to 0. Now x double dot plus k by m plus ms by 3 into x equal to 0. So now we can compare it like x double dot plus omega n square x equal to 0. So we can find the natural frequency omega n equal to root k by m plus ms by 3. So this is the final expression for the natural frequency of a spring mass system with a spring having mass with mass density rho. So what we see, if we have massless spring, so ms equal to 0, so that's why we get the natural frequency omega n equal to root k by m. But if we have some spring having mass ms, so the 1/3 of the mass will be accounted to calculate the natural frequency of the system. Okay, now we will take another example of the system to use this energy method to find the natural frequency. So let's take the another example. So here we have a U-tube manometer that is open to atmosphere, and there is a liquid column of L, length L here. Now if we want to disturb this column by pressing it with certain this liquid, by if we press it with X here, okay, so we are pressing here and then we want to see the free vibration of this liquid column, and let's assume that at certain instant of time the liquid column is here X, and because of the law of this conservation of the mass, the same mass will be raised here. If it is X here, it will be X here, so this will raise here X. Okay, so now we have to apply the energy method to find the time period or natural frequency of oscillations of this liquid column. So here we will have first let's have the kinetic energy. So the kinetic energy of the system, kinetic energy of the system, and let's say the density of the fluid, density of the liquid. And A is the area of the section of the tube. Okay. So kinetic energy of the system is half into, so each point of this column will have the same velocity x dot at that moment, and so the total mass half into rho into A into L into x dot square, half rho A. So rho is the density of the liquid, and so multiply with the volume, that is area into the L, so the total mass into x dot square. So this is the kinetic energy. Now the potential energy. Potential energy of the system. So first let's find this potential energy. So it is like we have this mass and kept here, so we will have, if this is the Cg of this mass, so x by 2, and here it is raised, so it is raised by x, this mass. So that mass is rho times A into x, so rho Ax, this mass is raised against gravity, so mg and into x. So this is the potential energy. Now we have this kinetic energy and potential energy. So this is T. So T plus U equal to constant. So T is half rho A L x dot square, and this is rho A G x square equal to constant. Now we have to differentiate, so let's differentiate this with respect to time. So half rho A L, so this is 2 x dot x double dot plus rho A G 2 x x dot equal to 0. So we have, so rho cancel out, A cancel out, we have x dot, so it is cancelled out, so this is 2, it is cancelled out, so x double dot plus Lx double dot, so here is Lx double dot plus 2gx equal to 0. So here we can write x double dot plus 2g by L x equal to 0. Now we compare it, this x double dot plus 2g by L x equal to 0, we can compare it with omega n square x equal to 0. So we find that omega n equal to under root 2 g by L, or omega n equal to 2 pi by time period t. So t equal to 2 pi upon omega n, so that is 2 pi root L by 2g. So this is the time period of the oscillation. So here we see that by using the energy method, we have to compute the first the kinetic energy of the system. So kinetic energy of the system means because kinetic energy depends on the mass. So if there is mass in the system, so all that system we have to consider, and system means the kinetic energy, the sum of the components of this system. So for example, in the previous case we had the spring and we had the mass, both were having mass. So we consider the kinetic energy of the both systems. In this case we have only the liquid column that is having mass, so we got only one component of the kinetic energy. So we have to find the kinetic energy of the system and then the potential energy of the system. We do T plus U equal to constant, we differentiate it, and after differentiating we get the equations that lead to us to the equation of motion, and from that equation we compare it like x double dot plus omega n square x equal to 0, and we find the natural frequency of the system. Okay, thank you for your attention and see you in the next lecture.